Assalamualaikum and hi everyone. Welcome to Module 3, which is about antenna design, simulation, fabrication and testing. So there are many ways to design an antenna, either by using cut and trial approach or by using simulation software. Cut and trial approach only works for simple antenna, while simulation software is much more accurate and working for complex antenna. There are many types of antenna software available, such as CST Microwave Studio, NC's HF SS, and FECO software. But these are pre-purchased, which are quite expensive. However, there are other free software, which one of the example is 4NEC2, which is developed by antenna designer in order to design antenna for free. Before students try to design an antenna, they need to understand what is or what are the antenna parameters. So, antenna design and simulation was carried out to get the optimum results of antenna parameters, which will give the best performance for the targeted application. So, antenna parameters or antenna results include return loss or S parameters, voltage standing wave ratio VSWR, gain, directivity, radiation pattern, and also current distribution. So, all this result depends on what do you plan or what is the desired antenna that you are planning to design. So how to know whether the antenna is good or not depends on the antenna performance. So antenna performance can be expressed in terms of size. The first one is size. The second one will be impedance or Z. The third one will be efficiency of the antenna. Okay, so in terms of the size of the antenna, so antenna usually expressed in terms of wavelength. So wavelength or lambda, it is equals to C divided by F, where C is the speed of light, which it is equals to 3 times 10 to the power of 8 milli per second. And F is the frequency of the antenna that you are planning to design. So for example, if you want to design antenna for Wi-Fi application, so the Wi-Fi application only works at 2.4 gigahertz. Okay, so that's how you are going to design the antenna for specific frequency and for specific application. Okay, in many cases, the antenna size is usually around 0.5 lambda. Okay, and for number 2, impedance, or sometimes what does it mean by impedance? Impedance, antenna impedance can be expressed in terms of the real value or resistance plus X, where X is the reactance. Okay, so the impedance of the antenna, it is equal to the voltage divided by the current. across the antenna. In many cases, the antenna need to be designed which its impedance is equal to 50 ohm. This in order to ensure that it is matched with other cables. So for good antenna, so the VSWR should be lower than 2 and the return loss should be less than minus 10 dB, where dB represent the decibels. So I'm going to show you later how a good antenna will produce this result. Okay, and the third one, antenna performance can be described in terms of the efficiency. So efficiency, it is equal to the radiation power, because the purpose of the antenna is to radiate power to the space, while divided by the input power that flowing into the antenna. So good efficiency, it means that the efficiency is more than 50%. The fourth one, the antenna performance can be described in terms of the radiation pattern, whether it is radiated in omnidirectional or whether it is directive antenna. So omnidirectional, it means that, so for example, you have a mobile phone. For example, long time ago, you have mobile phone with a wire coming out of the cell phone. So this wire is an antenna, so it will radiate the power equally to all the direction. While if you have another antenna, for example, represent here, so you can see that the maximum radiation pattern is pointing towards 0 degree. So it means that this is directive antenna. Okay, and the fourth one will be bandwidth, and the fifth one will be bandwidth, and the sixth one will be gain. So good antenna, for example, it depends on the application. Sometimes if the application requires antenna gain which is more than 3 dBi, 9 dBi, and so on, so you can design this one by using antenna software. So there are many methods in order to design an antenna. So for example, the first one will be cut and try approach. So this one is based on the theoretical calculation. So and it is simple analysis, and it is only works for simple antenna. The second method is by using 3D full wave electromagnetic software. For example, like CST Studio Suite, NSYS software, FICO, ADS. However, you need to subscribe this one. There are other free software in order to design antenna. For example, like NEC software. Okay. Before you start to design an antenna, you need to know which application that you are planning to design antenna. So as I've mentioned before, different type of application has different frequencies. So for example, like TV and radio broadcast, it is around in radio frequency range. While for mobile phone, for example, long time ago you have a GSM. So GSM at 900 megahertz. This is 2G. Okay, and for 4G LTE, it is at 2.6 gigahertz. So this is at another frequency. So that's why the allocation of this application or frequency spectrum has been has been proposed by the uh, government. So for example, for Malaysia, the electromagnetic spectrum, according to certain application, has been proposed by MCMC, or in Malay what we call it as KFM, Suruhanjaya Komunikasi Multimedia Malaysia. So for example, MCMC has proposed that if you want to, for example, if radio station want to broadcast their radio channel, for example, like Hits FM, what else, Surya FM, Era, and so on, they must be within certain range. So for example, MCMC has instruct, if you want to for radio station, if you want to broadcast Era FM, it is at 103.3 megahertz. Alright, so this frequency allocation has been allocated by MCMC. However, MCMC, the allocation of the spectrum by MCMC must be in line as well with FDC. Okay, so that it is compatible with other country as well. Okay. So, after you already decide which application and which frequency that you are going to design your antenna, so you can start design your antenna. So this is this flow chart here shows that the antenna design using cut and try method, the first method, okay, without using the software. So the first one will be choose frequency first. For example, I want to choose frequency at 2.4 gigahertz, which the application is for Bluetooth, Wi-Fi, okay. And then the next one, you need to choose a conductor. So copper is a good example of conductor. Another type will be silver or gold. Gold is quite expensive, so copper should be suitable in order to design an antenna. So you can purchase copper from the hardware shop, okay, in order to design an antenna. And then, for example, in many cases, the antenna size is usually around half wavelength or 0.5 lambda. Okay, so you can calculate or calculate the wavelength of that antenna, where the wavelength it is equals to C over F, and C is equals to the speed of the light. So in this case, I try to design antenna with monopole antenna with the length size of 0.25 lambda or quarter wavelength. So the length of the wire is around 3.06 centimeter at frequency of 2.45 gigahertz. The fourth step will be that you need to cut the wire with the length of the size of 0.25 lambda. And then after that, you need to build a ground plate from a copper plate. So after you cut the antenna, the size of this one, for example, like this one is your antenna. This is a copper. Okay, this is the fourth step. And the fifth step, you need to build a ground plane under this wire. Okay, So you can build a ground plane from a copper plate. That's the 5th step. And the 6th step, you can drill a hole for the copper plate. And then the 7th step, number 7, you need to trim the coaxial cable. So this is the coaxial cable, which from number 4. Okay. And then number 8, so you need to feed the copper cable through the ground plane. Okay, which is you need to feed from number 4 into number 6. And then for step number 9, you need to reveal the signal conductor. And step number 10, you need to solder the wire in order to tie the conductor cable together with the ground plane. And then number 11, you can see that the antenna is ready for you to use. So the second step to design antenna is by using 3D full wave simulation software. So similar like the first method, cut and trial method, you need to choose the frequency first and type of antenna. Okay, for the first step. The second one is you need to choose the software, the available software. So if you do not prefer to purchase, you can download the free trial software, okay, in order for you to design antenna. And the third method will be you need to select the material, for example FR4 or Rogers. This material are good selection in order to design the antenna. The fourth one will be you need to create substrate and ground. The fifth step, you need to create patch and feed line. The sixth step, you need to assign excitation and boundary. The seventh step, you need to run the simulation. After you run the simulation, and you can check whether your antenna simulation has met the target or not. So you need to check the result whether it meets, whether you design a good antenna or not. And after that, if you already meet the target, for example, like your antenna has already has VSWR which is less than 2 and the return loss is less than minus 10 dB, then your antenna is ready to use or ready to go for fabrication. So this is antenna design using the full wave simulation software. So this for example, I've already choose the frequency, which is the frequency is at 2.4 GHz, and type of antenna that I choose is inset feed patch antenna. So the diagram or the structure of this inset feed patch antenna is shown in this figure 1 and figure 2. Okay, figure 1 shows the top view of inset feed patch antenna, and figure 2 shows the side view of this inset feed patch antenna. And as you can see that each of the structure, it has symbol which is W, L, WP, WS, LS, LP, WF, HC, H, and so on. So this represents the dimension which is already calculated using theoretical analysis. Okay, so however, to make our life easier, So I've just presenting these parameters with their dimension, which is supposed to create a good antenna at 2.4 gigahertz. So the antenna dimension is represented in table number 3, table here. So antenna dimension represent the parameters for each of these symbol and its dimension in millimeter. So you are going to see later on how to design this antenna using full wave simulation software. And the materials that we use for this simulation represent in table which shows the material and the color code. So the material, the color code with in purple represent the copper material, while the color code of green shows the FR4 material. So this is how the antenna design of inset feed patch antenna at 2.4 gigahertz. So this is the finalized design using CST Studio Suite. You can see that on the left side represent the working directory, and the center pane using the antenna full wave simulation, and the bottom one represent the result navigator, and on the bottom right side shows the simulation progress. So after you already design this one, you can click the start button in order to run for the software to run the simulation. So after a while, the simulation stops and the results of this antenna appears. So for the next few slides, going to show you the simulation results for an inset feed patch antenna at 2.4 gigahertz. So the first important parameters, or the first important result, whether want to know antenna is good or not, is that you can see from the return loss or S parameters, which is shown on the first figure on the left hand side. So the first figure, as you can see, that this is the S parameter for or return loss result of your antenna, of the design antenna at several frequencies starting from 1 gigahertz to 5 gigahertz. So you can see that there is a low dip in S parameters, which shows that the antenna is working at 2.4 gigahertz. So you can see that the return loss here is actually less than minus 10 dB, which it is equals to minus 20 dB at 2.4 gigahertz. So it shows that this antenna is good at 2.4 gigahertz. So next parameters or next result, we are going to see how the surface current or current flows at the top of the antenna. So you can see here the current is flowing, which is represented by this color coded on color coded or color map on the right hand side. So the third one will be the 3D antenna radiation pattern. So the 3D radiation pattern of patch antenna here. So you can see the patch antenna shows here, and the radiation pattern is shows by this color. So you can see that the antenna exhibits directional or unidirectional antenna. Okay, it means that it direct the radiation pattern into this way. And this is your antenna. Okay. And the left hand side shows the radiation pattern in 3D, but on the right hand side it shows the radiation pattern in 2D. Sometimes it is easier to observe the radiation pattern of antenna in 2D rather than in 3D. So after the design antenna meet specified target at a certain frequency, then you can send the design to the fabrication. Okay, so from the previous antenna design, you can export the design into Gerber file, and you can send the file towards the manufacturer in order to fabricate the antenna. So antenna fabrication shall be carried out in order to realize the antenna. So these are the process in order to fabricate antenna from the Gerber file into the real fabricated antenna. So the first one on the left side shows the 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 antenna fabrication techniques, and the second one shows the masking process. The third one shows the fabrication that has been carried out, and the fourth one shows the realized antenna fabricated using Rogers material or FR4 materials. After you have already fabricated the antenna, so you need to test the antenna whether the measurement, the actual fabrication one, meet with the simulation design. Okay, so the antenna testing is carried out to measure the real performance of the antenna. So this can be measured using VNA or Vector Network Analyzer. So Vector Network Analyzer machine, which is shown here on the figure, it shows the S parameter or return loss of this antenna. So as you can see in this figure, this is VNA. So VNA is going to measure, this is the antenna. So it's going to connect with the antenna using this cable, and this is the antenna under test. So as you can see that from this measurement, the machine shows that there is a dip at certain frequency at 2.4 gigahertz. So you can say that the antenna, the fabricated one, is similar with the simulation design. The previous slide shows how the measurement conducted in order to obtain the return loss or S parameters of the antenna. For radiation pattern, it is a bit complicated. So the radiation pattern of an antenna can be measured using an anechoic chamber. So an anechoic chamber is used in order to measure radiation pattern, gain, and also directivity of an antenna. So figure on the left side, the left hand side shows it has transmitter, okay, and the receiver will be your antenna design or antenna under test. So the measurement for radiation pattern, gain, and directivity needs to be performed using an anechoic chamber. Why you need to use an anechoic chamber is because you want the radiation pattern, gain, and directivity of your design antenna are not interfered with other interference, for example from other device, radiation pattern from other device, such as, for example, if you have another Wi-Fi or Bluetooth from your laptop, so you don't want other equipment interfere with the result of your radiation pattern. Okay, so to summarize all of this module, so this module introduced participants regarding the antenna design either by using cut and try approach or by using full wave simulation software. So the participant will be given an exposure starting from scratch to design antenna up to fabrication and also measurement. Thank you so much for watching. Please, if you have any further question, you can refer to our website and our research group website. Thank you and wassalam.